If you remember, I told you the church, the supervisor of the Turing, was the guy who worked on the Lambda Calculus, and it was an interesting topic. And altogether, they are very similar to the Turing machine. They are a little bit different in terms of the way they talk about the things, but they are talking about the same thing. What is the Lambda Calculus? Lambda Calculus is a model of computation. It was invented before the Turing machine. Okay, invented by the church in the early 1930s. Lambda Calculus and Turing machine are equivalent in the sense that any function that can be defined using one can be defined using the other. Okay, so like I said, they are doing the same. They say it is possible to compute some sort of the computation using the Lambda Calculus or using the Turing machine later. The difference is in the Lambda Calculus, we don't have any internal state. The machine doesn't have any internal state at all. But in the Turing machine, as you can see, in the automata, they have the states, right? They have some state, and by taking different symbols of the input, we move from the states to other states. So that's the only difference between Turing machine and Lambda Calculus. So in Lambda Calculus, you don't have any internal state, but in the Turing machine, we have some sort of state, but they are equivalent in the sense if a specific computation can be defined and a specific function can be defined using the Lambda Calculus, we can solve it and we can compute it using the Turing machine too, the other way around. So that's the analogy between them. So what is the Lambda function? If you remember in Haskell, we at some stage we showed some function. You remember in Haskell we had some function definitions. We used to define the function. You remember we had the declaration of the function. We used to say that's the function from this type to other type, and then we used to say, okay, for this function that's the body of function. If that's the input, we remember the syntax, and then that would be the output and the calculation. And then some stage we used to mention it is possible to have a function inside the function. And at some stage, we used to say, okay, that's a function, but there is no definition similar to what we talk about in the Haskell. That was the Lambda function, if you remember. So I just wanted to recall what we talk about in the Haskell function about the Lambda function, but we will see that in here. So in the Lambda function are defined something like that. So that's the syntax of the Lambda function definition. You have the Lambda symbol in here, and then you have the input, and then you have a dot, and then you have the function. So that's the Lambda function, which calculates for you the sum plus one, not the summation, only the plus one. So that means if that's the function, if you receive x as the input, then the output would be that input plus one. This defines a function of one argument whose formal parameter is named x. The function body is x plus one. Note that the function has no name. So that's the difference between what we used to do in Haskell. In Haskell, we used to use a name for the function, but it is anonymous. Like I said, in Haskell, we talk about at some stage. If you look at the slides, if you back to the slides, you will remember we have talked about that at some stage. So, and that's the way we apply some argument to the Lambda function. Lambda calculus, Lambda function, okay? So if that's the function, then that means that would be the argument. The argument it will be applied to the function. Is the function, is the argument, and the entire thing itself is a Lambda expression. That's all. So if you see something like that, that's a Lambda expression. In exam, I may say the Lambda expression, blah, 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 is something like this, like the following, okay? So that's the whole story. And then a Lambda calculus computation involves rewriting. You remember that in Haskell we had the same thing. Basically, that's the concept of the functional programming. We rewrite the things. You remember we said we simplify the expression, the function, stuff, etc. So if we have something like that, we will say, okay, what would be next? The next would be we will put the argument into the input, and then what would be the solution? We will get the output. We can think of rewriting as replacing all occurrence of the formal parameter x into the function with the argument. Okay? So that's the syntax. The syntax of the pure Lambda calculus is as follows. The variable is Lambda expression, lowercase letter, like I said, the Lambda unit view. If m and n are Lambda expression, then so each of the following. M we can put parentheses around the anything. You remember I said that's a lambda expression. Parentheses will show us how we can show m should be a lambda expression there. Lambda id m, we can define a function whose formal parameters is id and whose body is m. We talk about that. M, and we can apply one lambda expression into another. We can have two lambda expressions. Okay, so that's very interesting topic of how we implement the recursive function. We can apply the second lambda expression to the first one. So m could be something like a parenthesis of lambda blah 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 like this guy, and then instead of the argument, it could be another lambda expression. It could be another expression lambda blah 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 blah, and then that means very similar. It works very similar to what we did in here. That would be the argument. That means you will apply this argument to this guy and you calculate everything. Okay? So that means we can apply another lambda expression to the first lambda expression. We can apply one lambda expression to another. M is applied to n application. Application, that's very important. Application is left associative. What does it mean? If you have these guys, that means A, B, and then C, not A, B, and C. So that means if you have something like that, that means you need to apply A to B first, and then you need to apply C to these guys. The other ways around is false, okay? Is right. So application has higher precedence than abstraction. Means what does it mean? If you have something like that, that means it would be like this. So if you have lambda x and then AB, if you have lambda x and AB, it means it is lambda x AB, not lambda x A and then B. So it doesn't mean this guy, it could be the body of this. This is wrong. This means A is the body of this lambda expression and then B is applied to that. It is wrong. It should be like that. So that means AB is applied to this lambda expression, right? So, and that's the abstract syntax tree. You are familiar with the abstract syntax tree, which we use in the coding and in compiler course, okay? Compiler module. So that's the Suhula story. If you have a lambda expression like this, and then the abstract syntax tree for that would be something similar, something like this. So it would be the apply, and then you have the lambda and the argument. For the lambda, you have the input and what is going on, summation, and then for the summation, it's something like that. And then if you take the input, it would be the summation. You will have apply lambda and argument, or what the lambda is the input and the summation, what the summation is the x and y. So then if you have tree, you will apply tree in here, you will jump to this guy. It is equivalent to 3 plus 1. Okay? We rewrite the abstract syntax tree by finding the application of function to the argument. For each, we replace the formal parameter with the argument in the function body. To do this, we must find an apply node. Its left child is a lambda node, since only lambda node represents the function. Okay? So that's the way it works. That's exactly the same way we did in here. We tried to simplify. We tried to rewrite. In the syntax trees, that's the case. You implement the whole lambda expression in the tree and try to see how we can sum up and get to the answer. So it will be the solution then. So if I have, see, that's an interesting case of lambda, that's A, that's M, and that's N. See, that's M and N. So that means I have for this one, I have an apply, lambda and apply. Why? Because this lambda guy has another lambda, which is by itself is apply. So I'll keep it apply. So let's implement it into the tree. That's lambda, and the argument is 3. And then for the lambda, it is y, the input and the operation, y and the operation, and for the operation, it is y and 2. Okay? And then for this guy, I have the lambda and very similar to this guy, lambda and summation. And for the summation, I have x plus 1, right? I have the lambda and apply. Instead of 3, here you can see I have lambda and 3, but here I have lambda and apply. Why? Because the argument is not a number to put the number. The argument by itself an application, so I should put apply in here. But for this guy, the argument is a 3, is a number, so I can say 3, right? So we can simplify it. We can simplify and say, okay, I will go in here and put in here. I will calculate this guy, which is 3 plus 2. I put 3 into this guy, and all the rewriting the whole process with 3 plus 2. And for this one, which is 5, and then I have this simple guy, it means 5 comes in here. I have calculated this part. So the whole, these things and this thing and this thing all together is, I have calculated this guy, which is 5. And then I have lambda expression, which is lambda x dot x plus 1 and 5, which is this guy. And then I calculate it, which is 5 plus 1. Like I said, this thing is equivalent to this one. So this guy is equivalent to 5 plus 1, which is 6. And then that's the answer. So in the exam, probably I may ask, please write down for me. Of course, it is hard to do that in the online exam on Einstein to ask for that, but I may hack it and find the solution how to do that. Okay, so that's the whole story of Lambda Calculus. What is the story of reducibility? Reducibility is the story of if you can reduce a Turing machine A or computation A to a simpler one. A reduction is a way of converting one problem to another problem. Everyday example reduction. Suppose we want to find your way around Dublin City. Okay, this problem can be reduced to finding a map of Dublin City. So if someone asks you, say for example, some old person in the city asks you, son, do you know, or daughter, do you know where should I go to this area? That's a problem, right? And you convert to reduce that problem to another problem. You think with yourself, can I have a map to look at the address and find a solution? Exactly, you can do that. So instead of trying to solve this problem, you solve this problem. And then reducibility always involves 2 problems, which we can call A and B. If A reduces to B, we can use a solution to B to solve it. If you find the solution in the map, then that solution would be solution to the first question. That would be a very interesting example we talk about. So note that saying A can be reduced to B does not say anything about whether or not A or B are actually solvable. We are not talking about if they are solvable, okay? That's exactly, we can come back to that example. If that person asks you, how can I go to that specific street? You can say, okay, can I find a map to do that? Yes, you can find. Okay, so you have converted, you reduced problem A to problem B. But is it possible to solve the problem B? So reducing and reduction doesn't mean necessarily problem A and B, they are solvable or not. Probably you may not have internet connection there, or that specific location is not available on the map, and so on. So what would happen? The thing that would happen is it is not solvable. So although you have reduced the problem A to B, but it doesn't mean necessarily you make the problem solvable. So that's the whole story. But usually it helps. Another example, problem A, calculating the area of the square. Is there a problem B that A can be reduced to? For example, measuring one side of the square. Someone asks you, can you calculate the area of the square? Someone which doesn't know that much mathematics. And you say, okay, I know how to calculate B, but I need to calculate the length of the one side of the square. So can I measure one side of the square? So it could be probably a very big far. So you say, that's not easy. If I plot it on the paper, I find some solution for that to solve the problem. And I can reduce the problem. But that's the question. Sometimes you have the problem. Let me bring you a fun example. During the European project, which I was the manager of the project, we wanted, at some stage, to develop an application for a drone. Then we wanted to know that was an embedded system platform that used to work with the battery, okay? We wanted to know what is the weight of that board and battery or everything together. And we wanted to estimate for how long the drone can work with the battery, okay? That was really up to the weight of the drone and the load connected to the drone itself. It was in the data sheet of the drone, okay? Then we didn't have any scale in the office to calculate the drone. Somehow I reduced the problem. I said, if instead of doing that, can I measure that with something else? So I tried to use the physics for that. I will find a picture of that and share it with you. So what was the solution I came up with? I started using a ruler, okay? And you know that's in mathematics, in physics. If you have a ruler and if you have a point, you can hang the ruler from that point from somewhere. And if it is in the balance, it will stay completely horizontal. If you connect two different loads in two sides of the ruler, then the balance would change. If you hang the ruler exactly from the middle of the things, and if you load two loads with this exactly the same weight, it will stay balanced. Okay, but if you change the load of one side, then the ruler will start to tend toward that specific side. Or if you change the base where you hang the ruler from some sort of the static point, then again the balance would be lost. Okay, so I tried to find the solution. I knew the weight times the length of that specific, the one side to the middle to the point which I hang the ruler is equal to the other length times the weight. So I hang the board from one side and I hang another specific weight like chocolate or something like that, which I knew roughly what is the weight on the box. I hang it from the other side and I try to come up to the specific point which I receive to a specific balance, horizontal ruler. Okay, and then I measure on the ruler what is the length of this side, what is the length of this side, what is the weight of this guy, the chocolate and stuff, etc. So the unknown was the weight of the board. And then I could measure it. And then afterward, I brought it home with myself and I weighted it, and it was like a fraction of gram. It was really interesting. So I reduced the problem, as you can see, myself. Okay, let's jump to the rest of explanation. We are in the shortage of the time. Okay, if A is reducible to B and B is decidable, then that means A is also decidable. That's very good. So equivalently, if A is reducible to B and A is undecidable, then B is also undecidable. A method to show that the problem A is undecidable is show that some other problem is undecidable. So that's a very interesting idea. Like I brought you an example from the real life, you can probably find a lot of situations in real life we use the same. Okay. The next topic is this another kind of automata, which is called the cellular automata. That's very interesting. The cellular automata is a collection of color cells. You have a grid of color cells. Each cell has a state, and this state can shown by a color. It's common for each cell to only have two possible states and to print this state black and white. So each cell can have two states. And we can print it in, like I said, showing color and print it in black and white. The colors can form shapes. As you can see, they have kind of pyramid here based on the state of the cells in here. It can be black or white. Okay. The shapes created by the automaton can evolve and change through a number of discrete time steps. Okay, the steps operate according to the set of rules based on the state of neighboring cells. So we have a grid. Grid consists of the cells. Cells can have states. States can be shown with the color, can be number of different states, and we can evolve. We can start with very specific, very initial configuration, could be something like that, anything, and then we can move to other configuration based on the rules we have. Okay, so cellular automata come in a variety of shape and variety of varieties. One of the most fundamental properties of the cellular automaton is the type of grid in which computed. We can have only one-dimensional. It could be just one row of cells, which is one-dimensional cellular automata. In the two-dimensional shapes like squares, triangles, hexagon grids can be created. You can have any kind of the things. Cellular automata may also be constructed with Cartesian grids and arbitrary number of dimensions. Okay, as stated already, each cell has a state, different state. They can have different colors. The number of distinct states could be K. K could be 2, which is binary. So if we have black or white, which is binary, cellular automata, okay, and for that, such automata also called binary automata. We'll talk about that, and the number we can assign is color 0 is for white and color 1 is for black. Cellular automata that have a continuous range could be continuous, could be from real numbers from 0 to 1 or anything. So that could be another type of cellular automata. Okay, and like I said, we start from very specific configuration and we move to other configuration based on the state. If each specific cell could be black or white, could be in any of these two states, okay? And then what could be the next state of that specific cell depends on the rules. And based on the rules, we can do different things, okay? So one of the, I'll share with you some videos about that. One of the interesting example of cellular automata is Game of Life. You know that game, and it is available in the market. You can buy it, you can play it on computer. The Game of Life is a well-known cellular automaton that consists of the infinite grid of cells, the square cells, okay, which could be black or white. The color or state of each cell is alive or dead, okay. The specific coloring of the entire grid is called the configuration, okay. There is a local update rule which we will talk about. What is that rule? According to the update rule, the new state of a cell only depends on the current state of the cell itself and its nearest neighborhood. So I'm in a specific cell. What is my next step in the next configuration? It's completely up to the neighbors. I will have 8 neighbors, isn't it? In a 2-dimensional space, if I'm in a specific cell, I will have 8 different neighbors around myself, because that's a grid of 3 by 3, which is 9 cells. 1 cell in the center is my cell, so I will have another 8 cells, okay? So a living cell, a cell which is black, stays alive if and only if there are either 2 or 3 living cells among the 8 surrounding cells. So if among all the neighbors only 2 or 3 of them are alive, then that aspect, then my cell also is stay alive for them. If a cell has less than 2 living neighbors, death by isolation will happen. More than 3 living neighbors, then death by overcrowding. So if I have more than 3 alive neighbors, I will die. If I have less than 2 alive neighbors, again I will die, okay? A non-living cell becoming alive if it has only 3 living neighbors, okay? All cells use the same update rule. This changes the colors of the grid, so configuration changes over the time. The process is then operated over and over again, which creates a time evolution of the system, okay? Objects from different categories merge when Game of Life is started in the random initial configuration, okay? That's very, very interesting. During the evolution, the objects interact with each other through collision with gliders and so on. So I don't want to go through that. So that's the whole story. And there is also, okay, so Game of Life is remarkable because the local update rule is extremely simple. However, the long-term behavior of configuration is unpredictable. Conway, Game of Life inventor, showed that it is undecidable. You may say, why you are talking about the Game of Life? Why you are talking about the cellular automata? Because that's an example of if that a specific problem for machine is decidable or undecidable. You remember? We talked about the Turing machine. If it is halting problem happens in here or not. If that a specific problem is decidable or not. And then the Conway guy named Conway showed that it is undecidable. If a given finite pattern eventually dies completely out. Where finite pattern refers to a configuration in which the number of living cells is finite. In other words, there is no computer program and never will be any as its existence in logical contradiction that takes an input of a finite pattern and always correctly determines if the input pattern eventually dies out. So that's the reason why it is something like that, okay? So there are some sort of situation like still life, like oscillator, like spaceship, like ground, which you can read through that. A fixed point pattern, the update rules keeps each cell unchanged. That's the situation that a specific cell stay unchanged, oscillates, and so on, okay? So that's the story. And there is one video in here, but I have another more interesting video here for you. I will run it for you. That's the explanation, and let's look at the situation. So that's an example. As you can see, that a specific configuration, and then that a specific configuration, as you can see, works like that. That's another specific. That it looks like that's oscillator case. You can see it oscillates and it is repeated. So, and then you may have other cases. You may have other cases. See, that's really interesting. That's really interesting. See? Interesting pattern. So it gets bigger and bigger. It gets bigger and bigger. That would be interesting. That's the beauty of the computer science, which we are not talking about that much in computer engineering. In science, we talk about most of these things. Okay, so look at this guy. That's really interesting. Okay, I will share with you this video, and then yourself you can look at different situations and do that. I really wanted to look at that. They are writing the things. Interesting. Yeah, so I really wanted to define some sort of the project as the bonus for you guys to do some sort of the research. Maybe I can define it later and put it into the website. And if you are interested in these cases like that, you can find the real world problems and prepare a kind of presentation or write some sort of the code for that, etc. And I can consider some sort of the bonus for that. I will ask that in the pool later. And if students are happy to do that, I will do